Well, welcome to Functions and Inverses, which is a guided exploration designed for Mathematical Methods, Unit 1. Now, I'll be speaking about Part 1, which is about understanding the inverse of a function. So, for this part, students will need the student activity worksheet together with the pre-prepared TI-Nspire document Inverse 1. Now, Part 1 is very user-friendly, and it's suitable to be used as a self-paced homework task by students. Now, the learning objectives for Part 1, it's to use dynamic features of TI-Nspire to interactively explore the concept of the inverse of a function and its graphical interpretation, the conditions for a function to have an inverse function, and we'll also have a look at an application of inverse function, a very practical one. All right, so the first activity involves looking at pointwise reflection in the line y equals x. So we're starting with a simple linear function. So it's a function with rule f of x equals 2 brackets x minus 1. And we can see that the straight line cuts the x-axis at positive 1, which we would expect because it's a translation of 1 unit to the right of f of x equals 2x. And if we were to expand that, it would be 2x minus 2. So that's, as we can see, it cuts the y-axis at negative 2. But we have a point P, and it's reflected in the line y equals x, and I can animate that point and stop it at any time. And any time you stop, the thing that we're hoping students notice is that the effect of the reflection in the line y equals x is that the coordinates of the point, every point on the line, they get switched around. The x becomes the y and the y becomes the x. And I can get a trace of that. So to get a trace, you go to the point you want to trace and control menu for the context menu. You can get geometry trace, and it leaves a trace to see where the point has been. And it would be interesting to see what the equation of the reflected line might be, the line that contains all the points on the trace. So this is one I prepared earlier. And we can see that the trace is also going to be a straight line. And whereas the original line has a gradient, a rise of 2 for a run of 1, we see that it's the other way around in the case of the reflection. So already students should start to see a pattern that we go from a gradient of 2 to a gradient of a half. We can also see that whereas the x and y intercepts have now been reversed, so that the reflected line is now going to cut the x-axis at negative 2 and the y-axis at 1, the reversal of the original. And we can see what the equation might be. So we could write the equation. We know that it's got a gradient of a half, and it cuts the y-axis at positive 1. So let's see whether that works. And not surprisingly, that is the equation that contains all the points on the trace. Or if we wanted to have that in a different form, we could have a half x plus 2, and that would also fit in. And that would just be looking at it as a translation of y equals a half x. Okay, so let's see if we can generalize that and have a look at the pointwise reflection of lines of a more general form. They're still straight lines, but we've replaced the numbers with the parameters a and h. And students can manipulate the value of a and h using the sliders and change the value of a, and they can see both the trace and the original. And you get some interesting results, such as that one, and that one, and so on. And the idea is that students try and see if there's a pattern between the straight line that fits all of the points in the trace and the original. And not surprisingly, if students enter an equation of the form 1 over a x plus h, then it will, in all cases, match the trace. And what we're hoping that students will get from this is that one way that they can get the equation is by interchanging or switching the x and y values of the equation and rearranging to make the y the subject. That's what we're hoping that they get from this. So let's have a look at a practical example, which is looking at temperature records prior to 1972, when Australia recorded all temperature records in Fahrenheit rather than Celsius. So if we want to make a comparison between Fahrenheit and Celsius, we need to know how to convert. So the function shows the conversion graph for y degrees Celsius at x degrees Fahrenheit. So if students wanted to find what 30 degrees Fahrenheit was in Celsius, a number of ways they could do that graphically. For example, they could go to the menu and go to trace and graph trace. Just put in the number you want, and down the bottom they can see that it's about -1 degree. Change that number. If I wanted to know what 100 Fahrenheit was in Celsius, it's 37.8. I can see the coordinates down the bottom here. All right, so what if I want to go in reverse order? What if I want to know, for example, what 28 degrees Celsius is in Fahrenheit? I'd be doing the opposite. So one way I could do that would be to graph y equals 28, for example, and the point of intersection of the two graphs. So let's find the point of intersection. There's a number of ways I could do that. One way is to do it either through Analyze Graph and do intersection, or I can do it through the Geometry menu, intersection. And I can see that 28 degrees Celsius is 82.4 degrees Fahrenheit. Now, alternatively, of course, I could get the inverse function. I could swap them around, swap the x and the y. So this is where students can use the graphs page to get the same results, to verify their graphical results. So here, for example, I could solve for 28, solve 28 equals f of x, and of course I could get a rational approximation. I could get the decimal equivalent of that, and of course it verifies the result. So it shows that what I've really used is swap the x and the y. So that's the algebraic equivalent of what I did graphically. All right. Now, what I can do is get the inverse, and once again, students should have been able to see that if you swap the x and the y, you solve for y, then it's going to be 9 over 5x plus 32. right? So this time, if I have y equals the inverse function of x, in this case, we're talking about y degrees Fahrenheit at x degrees Celsius. So this time, I could use the trace direct. So to find what 28 degrees was in Fahrenheit. So I could do graph trace for this graph and 28, and I get 28 and 82.4. So we can see how we can use the inverse function to get the same result that we were getting by solving algebraically. Right, now we can ask other questions such as, at what temperature do Fahrenheit and Celsius have the same value? And once again, students could do a number of things, but they might say, well, hang on, if I want f of x to equal x. I want x and the y values to have the same. Or I could say I want the inverse function to equal x. I want the Fahrenheit to equal the Celsius, or the Celsius to equal the Fahrenheit. So in other words, I can do it by looking at the intersection between either the blue line and y equals x, or the red line and y equals x. And there's a number of ways I can do that graphically. One is to go to the geometry menu, points and lines, intersection points. So I want that one with that one, or I can do this one with that one, or indeed I can do the red with the blue. And interesting thing is that in this case, they all give exactly the same answer, negative 40, negative 40. In other words, negative 40 Celsius is equal to negative 40 Fahrenheit. And there's a number of other questions in the worksheet related to that conversion. And algebraically, students should be able to see that if they solve the equation simultaneously, it doesn't matter whether they do y equals x for f of x, or for the inverse function, which I've graphed as f2, or indeed whether I do f of x equals the inverse of f of x, I get exactly the same result in every case. And the last activity involves looking at a nonlinear function. So this time I'm going to see what the pointwise reflection of a parabola is, and we get a rather interesting result. And students can investigate what the equation might be, and they can look at relation graphing. So we can graph the relation x equals y. So if we go to relation and try again, x equals f of y. So I've swapped the x and the y, and we can see that that fits every point on the trace. And finally, students can have a look at restricting. We can see that that is not a function, the inverse is not a function, because for one, a vertical line will intersect more than once. So students can restrict the domain and see what the restricted domain is, such that the inverse is a function. So we can see that from x equals -1 or greater, the inverse of f of x is a function. Okay, so I'll hand over to Raymond now, who can have a look at part 2.
Okay, So what I'm going to do is I'm going to work through a couple of worked examples of function and an inverse. And what we want to explore here is where does the function and the inverse intersect? There are a number of possibilities that we'll look at here. So look at sort of 2 or 3 questions. This one is not exactly the same as the one on the sheet, so it's a different one. So what we're going to consider here is the function f of x equals 6 minus 2x, which again is a linear function. We want to find the rule for the inverse function, and we want to find the coordinates where both of these graphs, that's the function and its inverse, cross the coordinate axes. And we want to try to solve these 3 equations, where the function crosses the line y equals x, where the inverse function crosses the line y equals x, and where the inverse and the original function are the same. So I'll work through this on a calculator page. So because we're going to be looking at this function, I'm going to define that function as f1. So I'm going to use menu, actions, define. And I'll call it f1 of x, so on the calculator screen, then the graphs page will actually know about it. So that's my first function. Now, if I want to find where that function crosses the x-axis, that's when y equals 0, isn't it? So in other words, I have to solve the equation. So let's go menu, algebra, solve. And what do I want to do? I want to solve when the equation f1 of x is equal to 0 for x, so comma x. And that'll give me x equals 3. If I want to find where that function crosses the y-axis, well, that's simply the value of x equal to 0. So I'll just type in f1 of 0. All right, now we want to find the inverse function. To find the rule for the inverse function, what we have to do is we have to swap or x and y and then rearrange to make y the subject. Now, a neat little way of doing that is to go menu, algebra, solve, solve f1 of y equal to x, but this time I want to solve that equation for y. Nice little idea there. So that gives me the rule for the inverse function. So what I want to do now is I want to define that one as f2. So I'll go menu, actions, define, f2 of x equal to, and I'll just press the up arrow to paste that one in there, but I have to press the backspace to delete the y equals. So that's the inverse function. So once again now, I want to find out where this function crosses the x and y axes. So we can type it in, or we can use the menus again. Menu, algebra, solve. What do I want to do? I want to solve where this is equal to 0 for x. That gives me x equals 6. Now the original function crossed the y-axis at 6. The inverse function crosses the x-axis at 6. What about f2 of 0? That's obviously 3. So the inverse function crosses at 3, whereas the original function was the other way around. So things, as we can see here, are getting swapped around. Let's try to solve where the function and its inverse intersect, and if they do intersect, is it on the line y equals x? Now, rather than typing the f2, I can also just go to the var menu and get the f1. So let's solve where f1 of x is equal to x, and we want to solve that equation for x. If I just press up arrow there, I could solve where f2 of x is equal to x, or I could even solve where f1 of x is equal to f2 of x for x. Now, in this case, all of these 3 equations give me the same solution as x equals 2. Since I also want to draw the graph of y equals x, I'll define that function f3 of x to be the line y equals x. All right, so I'm going to go on to a graphs page now. And if we just press up arrow, all of these functions are defined because the calculator page tells the graph page that they're there. So that's my first function. Let me just press tab again and press up arrow again and do the inverse function. And let's do it one more time just to get the line y equals x. Now, I'm going to just make this look a little bit prettier now by pressing Control Menu and just changing the attributes of this one to make it a dotted line. It just looks a bit nicer. Let's introduce some colors here and make the original line with a color of, say, blue. And let's let the inverse function, again doing Control Menu, let's have this color as, say, red. And we can move these labels out of the way a little bit. Now, I haven't changed the axes here. I'm using the same scale as the default scale here. The reason being is that you can see that these lines here look like they are reflections in the line y equals x, aren't they? And if we wanted to find the coordinates of the point of intersection, let's go Menu, Analyze Graph, Intersection. Now there are three graphs here, so I'll just click on that one and move my cursor to the left and the right, and we get the coordinates of the point of intersection, which in this case lie on the line y equals x as the coordinate 2, 2. Notice that this graph would cross at 6. Now another nice little feature that's now available in the latest version of TI-Nspire is to put more lines and more dashes on the coordinate axes. So if I go Control Menu here and now go to Attributes and come down to this option here, single tick labels or multiple labels. So that's a really nice little feature, and that we can see now that this graph crosses the x-axis at 6 and the y-axis at 3, and the inverse line or the inverse function crosses at x equals 3 and y equals 6. So a very nice little picture there. All right, now the idea behind this little activity is also to figure out if all functions and their inverses must always, or do they, or can they, intersect on the line y equals x? Can they intersect elsewhere? Do they have to intersect? There's some of the ideas that we want to think about in some of these next examples. So let's have a look at another example here. This time I want to consider the function minus 1 over x, which you know is a hyperbola graph. And once again, I want to sketch this graph, and I want to try to solve the three equations again regarding the function and its inverse. And we want to comment on some of these situations that are happening here. Well, once again, I'll do a similar thing. I'll go to a calculator page. Notice that this is a new problem, so my functions f1 and f2 from my previous problem are not known. So I'm going to define the same way I did before, Menu, Actions, Define, a function f1 of x equal to minus 1 over x. I'll use the template there as 1 over x. Now, this one doesn't cross the coordinate axes, and we'd like to know perhaps its domain and range. Now, the calculator does have a nice little feature where we can find the domain of a function. It's not available from any of the menus, but if you press the little book command or the catalog of all the commands, that will give me a listing of all the commands available on the calculator. I'll hit the letter D, so I'll scroll to all the ones that start with D and just keep pressing down arrow till I find the one that I want here, which is domain. There it is, and we can see it is domain expression variable. So if I just type in now f1 of x, comma x, that'll give me the maximal domain of this function, which is any real value except for 0. All right, so we know that this function is going to have the x-axis and the y-axis as vertical and horizontal asymptotes. Okay. So let's try to do the command that we did before, and that's solve f1 of y equal to x, and solve that for y. We get the same equation, y equals minus 1 over x. So what does that mean? Well, this means if I was to define this function as minus 1 over x, then what do we know about the function f1 and the function f2? They are the same function, aren't they? So what would happen if I tried to find the points of intersection between f1 and f2? It's going to happen here. True. Well, because they are the same graph, there is in fact an infinite number of points on the graph, which is the points of intersection between the graph of f1 and the graph of f2. Notice once again, I'll define f3 of x here to be the function x. And if we try to solve where the first function or the second function is equal to x or the function f3, then this time that tells me false. Perhaps we better have a look at the graphs and see exactly what's going on here. Well, there's my first graph. There's my second graph, which is the same as that graph. So they're both the same. And there's my line y equals x. So what's happening here? Well, the two graphs f1 and f2 intersect at every point, or an infinite number of solutions, and neither of them intersect on the line y equals x. So some strange things happening here. Let's have a look at one final example, which is the function negative x cubed. Let's try to find its inverse function and try to find out what's happening here when I want to solve the solutions of that function and its inverse crossing the line y equals x. So again, the same thing we're going to do. I will type in f1 of x equals minus x cubed. I will try to solve f1 of y equals x for y to give me the rule for the inverse function. Same steps that I've done before, I'm now going to solve or define that function to be the inverse function. Both of these have domain and range R, so we won't worry about the domains and ranges here. But also this time we need to define f3 of x equals x, so we'll see the line y equals x. What will happen this time when I try to find where the original function intersects the line y equals x, or f3? All right, so that one intersects at x equals 0. What about where f2 intersects the line x equals 0? Only at x equals 0. But what happens, it's easier just to press up arrow and edit these things. What happens where the original function is going to intersect its inverse function? This time I get 3 points of intersection. Okay, so let's have a look at these two graphs now. So there's my original graph, negative x cubed. Once again, we'll just play with that a little bit and make it nice, pretty blue color. I'll press tab to get my second function. We'll see the graph of that one. Let's just make it red color. And now I'll press tab again to sketch the line y equals x. And again, I can make that one dotted if I like. Okay, so what's happening this time? Well, we can also do this graphically. Menu, analyze graph. Let's find the intersection between the inverse function and the original function. They intersect, oops, let me move that one out the way. They intersect at the line on the point -1, 1. There's another point of intersection, I think, down here as well. So let's analyze graph and do the same thing again to find the point of intersection between these two again. So it looks like the function and its inverse intersect at 2 points. These 2 points are not on the line y equals x. There is another point of intersection between both these two graphs and even the line y equals x, and that's the origin here. So this time there is 3 points of intersection between the function and its inverse, but only 2 of them are lying on the line y. Only one of them is lying on the line y equals x. The other 2 points of intersection are not on the line y equals x. Okay, so there's lots of little interesting things that can happen here. You know, how many times can a function and its inverse intersect? Can it intersect twice? Could it intersect not on the line y equals x? Is there an infinite number of points? And we've seen that some of these examples are generating some of these questions. So I'll leave it for you in the activity to answer some of these questions, which are sort of true or false, or they're all true or false. So several students stated some comments regarding functions and their inverses and the number of points of intersection. So I'll leave the exploration there and let you think about these questions and answer them. So there's lots of statements here. Reciprocal and inverse are the same, are they? So there's lots of statements here. All of this is on the activity sheet for students, and you can have a think about these possibilities and things that can happen. So we don't want to give the game away too much here, but there's lots of exploration and lots of possibilities. And this is a bit of a common misconception, not only among students, but also some teachers as well, about the solution of the function f of x equals x, the inverse equals x, f of x equals the inverse. So, you know, we want you to explore these and think about what's happening with the function and its inverse. So I think I'll leave it there. Have we got anything else, Frank, that you want to add to any of this? I think we'll let the students work through this worksheet themselves to get some understanding and exploration to see the possibilities that can happen. All right, so thank you for watching, and hopefully when you work through this worksheet, you'll understand some more properties of functions and their inverses, and one-one functions to restrict the domain, as Frank was mentioning before.